seminars. So today it's my great pleasure to introduce Professor Hussein from the University of Boulder in Colorado. And Professor is going to talk about nanophononics metamaterial. I believe it's one of the first talk where we are going really to approach the nanoscale. And I leave you the Professor Hussein for his talk.
All right, so thank you so much. Thank you for the invitation to all the organizers, Sebastian and Bogdan and Muammar. It's really an excellent forum that you guys have organized, and very, very helpful, I think, for the metamaterials community. I think I've selected this background intentionally because here in Boulder, we were just a few minutes past sunrise, so 7 hours behind London. But I'm very much looking forward to sharing with you today this topic, which is what we call nanophononic metamaterials. This is a concept that we've put forward several years ago. In short, we call it NPMs. And in contrast to electromagnetic and acoustic, elastic metamaterials, nanophononic metamaterials is concerned with thermal transport. So this is essentially nanoscale heat conduction. And as stated in the title here, it is fundamentally based on local resonance. But perhaps what's most intriguing is that it fundamentally involves not just a few local resonances as usually the case, but numerous, and in fact could be as many as millions of local resonances. So this is not an exaggeration. This is really part of what an NPM is all about. So before I start, I just want to quickly acknowledge what I would say 3 generations of PhD students. I say this because they essentially came in sequence and passed the baton from one to the other. So Bruce Davis and Hussein Honarvar, and my current PhD student, Chia Nien Tsai. Okay, so sort of starting with a big picture point of view, we know in electromagnetics, the notion of a locally resonant electromagnetic metamaterial emerged as an artificial type material with unique substructures, usually or classically, I would say, the notion of a split ring resonator. And these substructures play a very important role in the long wave regime, in the sense that at long waves, you can look at this medium and view its effective properties. And of course, the effective properties, because of these resonances, can be quite remarkable, quite extreme. So in analogy, in the area of acoustics and also elastic waves, the notion of a locally resonant, similarly, a locally resonant metamaterial also emerged, where now the interest is in effective properties to do with acoustics and elastic waves like Young's modulus and density. And the very first demonstration was as shown here, based on having heavy inclusions coated with a relatively compliant material, and then that together being embedded in a matrix, and that's how you get these local resonances. So what I'll be talking about today is yet another analogy, and that would be locally resonant metamaterials for the control of heat, so nanoscale heat conduction. And this is, we've proposed this in 2014. Before I go into the details, though, I want to really emphasize that this should not be confused with the notion of thermal metamaterials, because I know that this forum has the term thermal in its title. So this is fundamentally different than thermal metamaterials. And on that, I want to just maybe take a minute to have a side slide on this issue here. So when we look at the notion of transformation optics, acoustics, and it followed that you can also apply the concept of transformation to heat transfer. a lot of people in this community, I'm sure, are familiar with this topic. Very elegant mathematical scheme that allows you to transform a field in the material itself and essentially mathematically produce heterogeneous and generally anisotropic set of material properties distributed in space, such that you effectively achieve some form of interesting phenomena. And this review article here by Steve Kammer, I think explained this very well. You can see in this schematic there, just in a nutshell, you start with a simple medium and you apply the transformation techniques mathematically. So you deform the media itself in a way as to achieve a certain function, for example, cloaking. And then you say, okay, in order to achieve that, in order to realize that, we require certain material properties in this region. You can see it there on the top right. And then you say, okay, if we have purely ideal materials that can realize these properties, then we'll introduce these materials with their spatial variation to recognize that transformation. But of course, realistically, you can't do that. So you resort to metamaterials, which would be an approximation, although still an excellent approximation, and allow you to achieve this transformation. So in thermal metamaterials, this process has been applied, whereby you can do pretty much the same thing to control diffusive heat transfer. So diffusive heat transfer is heat transfer that does not, that for all practical purposes does not involve wave propagation. So this is, in that sense, it's very different than optics and acoustics. And this is what is referred to as thermal metamaterials. And what I would like to say is that this is definitely not a nanophononic metamaterial. This is not what I'm talking about today. So with that note, aside, if we go back to this sort of a general picture, when we look at light and sound, when we look at metamaterials for electromagnetic and acoustics and elastic waves, usually we capitalize on the presence of one or few local resonances, and this is typically in the subwavelength regime. That's what makes it very, very exciting, and because you can have very small unit cells, and what you do then is using different techniques and depending on application, obtain these unique and remarkable effective properties. For a nanophononic metamaterial, on the other hand, as I said earlier, we're utilizing millions of local resonances, and this is not an exaggeration, and I'll explain as we go through the talk. Of interest is not just the subwavelength regime, in fact, the entire spectrum, including the super wavelength regime. And really, for the purposes of, for all practical purposes, and I'll explain that in a minute, we do not need an effective medium theory. So in a way, it's very different than acoustic and electromagnetic metamaterials, although we still fundamentally utilize the notion of local resonances. In terms of applications, we know, of course, that imaging, focusing, cloaking, and so on are the applications for the first two classes of metamaterials. For nanophononic metamaterials, the key application, I would say, is thermoelectric energy conversion. So this is conversion of heat to electricity, or vice versa in the solid state. And in principle, it can be used for manipulating other type of thermal properties, like the heat capacity, for example. Okay, so I want to start by diving in from the outset a bit into some details of the modeling, and I do this intentionally because it is critical when we're analyzing MPMs that we model at the nanoscale, truly at the nanoscale, meaning at atomic scale. Because if we don't do that, we will for sure we will lose much of the important physics associated with the problem. So this is just an animation showing you a few atoms vibrating and transmitting a wave. So just like in the continuum, we can represent this using a band structure. So we identify wave numbers and frequencies, and we use all the familiar theorems, Bloch's theorem, Brilliant zone, and so on. And in this case, we're using a large unit cell, so we're unfolding and hence getting these unfolded bands and so on. And of course, we can look at the modes just like we do with when we're looking at acoustic metamaterials. And in this case, of course, these are atoms. So this is a representation of the motion of some transverse mode, and this is a longitudinal mode, and so on. Now, this is, of course, a linear picture because it's a band. It's a linear set of dispersion curves. Although I should say that when we go down to the nanoscale, because of the nature of the interatomic interaction, it is essential also to be mindful of the scattering events. So this is perhaps yet another big difference with acoustic and electromagnetic metamaterials, in the sense that nonlinear scattering is really part of the problem. There's no such thing as a linear version of the problem. Although we can make the linear approximation just for the purpose of viewing a band structure, which can be useful, but once we, for example, simulate the model using molecular dynamics, for example, and predict properties like the thermal conductivity, then we essentially have to include the scattering. And this is this is directly related to the notion of mean free path and phonons interacting with each other non-linearly and so on. And I'll talk about that more throughout the talk. But so now that we realize that the atomic modeling is essential to this problem, I have a few slides here that goes through very systematically how we do that. So we're particularly interested in silicon for not just for practical reasons, because it's abundant and it's the key material in the electronic industry and so on, but also because it's actually very favorable from that very point of view of phonon scattering and mean free path and so on. It actually has a very long average mean free path for phonons, which allows us, or which provide us with a decently large window of opportunity for utilizing wave phenomena in a manner analogous to what we do with acoustic metamaterials. So and again, more about that in a few slides. So for silicon, the primitive cell is a two-atom primitive cell, and we can establish its primitive lattice vectors and corresponding Brilliant zone and corresponding reciprocal lattice vectors and so on. But it's more practical to actually consider what we call or what is known as a conventional cell, CC, because it has a cubic unit cell and a more workable Brilliant zone. So we will work with a conventional unit cell, and you can see here the Brilliant zone on the right, with in fact also the irreducible Brilliant zone shown, and using familiar notation and so on. So we can then take that conventional unit cell and create a building block with it. So this here is 2 by 2 by 2 conventional unit cells of silicon. Each CC has 8 atoms. So this 2 by 2 by 2 has 64 atoms. And now we have a very convenient building block that we can create our model with. So let's start with what I've shown you before. Let's start with a bulk model. So so this is just a schematic showing a bulk here on the left, and then on the right, just next to that schematic, is an actual image of the atomic model. And since it's bulk, we'll assume periodic boundary conditions in all 3 directions. So we have a 3D Brilliant zone, and these are the dispersions which I showed you before. So now we move to the bigger context. So as I said earlier, probably the most important motivation is thermoelectrics, and part of thermoelectrics is the thermal conductivity. So there is, for those who are familiar with thermoelectrics, there's a figure of merit which is basically tells us that we need a material with very high electrical conductivity but very low thermal conductivity. So we're going to focus on the thermal conductivity part. Our goal is to reduce the thermal conductivity, and this is this is the underlying motivation. But as I said earlier, there's other applications as well. So let's look at the thermal conductivity. It can be modeled in different ways. One very insightful model, I would say, is the Boltzmann transport model under the relaxation time approximation. And this model, what I like about it, it allows you to get a quite meaningful insights into the physics of thermal conductivity or thermal conduction and what constitutes the thermal conductivity of a material. This is an fundamental intrinsic property in condensed matter physics. So what this model tells us is that the thermal conductivity is a summation over all modes, so all these branches in the band structure, and in summation of all modes in the form of an integrand. And you can see the integrand here, or an integral, I should say, and this integral is over the entire Brillouin zone. And if we're interested in thermal conductivity in a particular direction, so the integration would be along that specific wave vector. And then when we look at the integrand inside that integral, it consists of a product of three components. So we have the specific heat, and then we have the group velocity. So the group velocity in this context, we know, of course, the group velocity is the slope of the dispersion curves. But in this context, it's important in the sense that it's a direct measure of how fast the heat can transport, and it contributes to the thermal conductivity. The higher the group velocity, the higher these slopes, the higher the thermal conductivity, and vice versa. And then the third component here in the product is the scattering time constant. So the scattering time constant that's the parameter that's to do with the nonlinear events that take place. So whether it's phonon-phonon scattering or boundary scattering, and essentially it's a time constant that tells us to what extent wave phenomena can take place. So we can use the group velocity multiplied by the time constant to get a mean free path. And what the mean free path will tell you is that on average, or not even on average, each phonon in principle can travel a certain distance before it scatters with another phonon and loses its wave character. But to the extent it can travel during that spatial length, which we call the mean free path, or correspondingly that time window that we call the lifetime, during this time it's actually traveling completely like a wave, and the band structure that we're seeing here is completely relevant. So this really adds to the complexity of the problem. And then we're dividing at the end, you can see here at the right, by V, which is the total volume of the unit cell, because this is an intrinsic property. So we divide by the total volume. Now, as I said, the group velocity is key there, and if we reduce it, we can reduce the thermal conductivity. You can see this directly in that formula there, and we of course immediately can recognize that if we reduce the dimension of the material, so go from bulk to membrane. So in other words, the model itself, it can be pretty much the same model, except now we only have periodic boundary conditions in plane, and out of plane it's totally free. Then we have a membrane, and we know, of course, that because of that phonon confinement that we'll essentially see a flattening of many of the curves. And from a continuum mechanics perspective, it's essentially a plate, and you can see the dispersion curves, especially the acoustic modes, they're flattening. We have the flexural mode and the shear mode, and so on. So one can look at this and say, okay, great. If we turn a bulk silicon into a membrane of silicon, we'll reduce the group velocities, and we're reducing it. In fact, we're reducing them everywhere, because as you can see, the formula in the top depends on the summation of all branches across the entire Brillouin zone, or at least in the direction of interest. So we're really, it's really a collective improvement that we're getting. However, though, I should say that even though we get this reduction, it's not good enough. So this is where the MPM comes into the picture. So once we add pillars, and very, very analogous to pillared plates and acoustics or elastic waves, but now, of course, it's an atomic scale. Once we add these pillars, not only we have this plate type dispersion spectrum, But we have these resonances that come into the picture. And these resonances, since now that they're at the atomic scale, we call them vibrons. So they appear just like in the continuum problem. They appear as straight lines, but we call them vibrons here, essentially inspired by the use of this term when describing standing waves, vibrational waves, and molecules. Because this is exactly what they are. Unlike phonons, which are wave number dependent, the vibrons are wave number independent, and they are standing waves associated with a pillar. But they appear in that atomic scale band structure, and not only that, they appear in abundance. They appear everywhere. So you can see all of these are vibrons, and that's where, you know, that takes us back to the title. There's millions of them in principle. So if we're thinking of, let's say, the unit cell, typically it's in the order of a few tens of nanometers. So let's say the pillar, let's say the membrane is 20 or 50 nanometers thick, and the pillar is has a square cross section that is 20 by 20 by, let's say, 400 nanometer. Then we're talking a huge number of degrees of freedom, because each atom has 3 degrees of freedom. So in total, we're basically talking millions, if not tens of millions of modes. And corresponding to the modes, to the number of modes that's stemming from the pillar, because it's the resonating structure, we get as many of those horizontal lines that totally really overwhelm the spectrum. So when we go back to the point of view of the thermoconductivity, we recognize that this is very useful, because then we have an opportunity to reduce these group velocity, component very significantly. Okay, so I want to now sort of dig deeper into this. So this is a picture that shows you in a little bit more detail. In red here, you can see the membrane without pillars. In green, the pillars. On the left, you have the frequency versus wave vector. We can differentiate and get the group velocity across the spectrum. You can see clearly that it's reducing significantly compared to the red terms. In the circle there is where we get the hybridization. So we're getting a lot of those. So as I said before, number one here is one mechanism that comes about from adding those numerous resonances. But there's another one. There's another equally important mechanism, and that is the notion of localization. So when we add a pillar, we add more atoms, so we add more modes, but these added modes, as we know, appear as horizontal lines, so they don't contribute to the group velocity, yet we're adding a lot of them, and then we're dividing by the volume, because it's as I said, we're seeking an intrinsic property, which is the thermoconductivity. So this process by itself also contributes to the reduction. And this picture here shows you 2 modes, one on the left, which is just a regular membrane, and you can see the atoms moving, and then on the right, a corresponding point where you have the pillar, and the pillar is resonating, but the atoms underneath are totally stagnant. So this is a video to demonstrate that sort of like visually. You can see without a pillar, and then when you have a pillar, indeed you get almost standstill in the atoms. And specifically from an atomic perspective, this is very interesting, because it's really probably unprecedented to have a situation like this, where a huge number of resonances can be employed to achieve a phenomena of this nature. There is actually a third element to it, which is the scattering. You remember from the thermoconductivity expression. So I will not spend too much time on that, but I'll just say that by running MD simulations, which incorporates the nonlinearities and the scattering and everything, more brute force, I should say brute force, as opposed to the dispersion diagram calculations, which is a linear approximation. When we do the MD and then take the velocity field of the atoms at equilibrium, and then there's a technique called the spectral energy density method, which allows us to transform this by Fourier transform into the frequency domain, and we can scan some of these modes and identify its peaks, and from there we can indirectly predict the level of dissipation, which correlates with the lifetimes. And you can see that the lifetimes drop, which we expect because of the introduction of pillars, and that's because the scattering environment, the phonon-phonon scattering environment changes. So that in itself is useful, because we know that if the lifetimes get less, the thermal conductivity get less. But then there's a danger that if the scattering is too strong, then the mean free paths will get so small and will lose the wave effect. So to test that, and this brings us back again to the benefit of silicon, it has a very large mean free path even in at room temperature. So to test this, we did the Fourier transform in both frequency and wave number space. And this is what we can see here. So a membrane, you can actually see the dispersion curves almost identical to what we get by the linear harmonic approximation, where we get the dispersion curves by eigenvalue analysis, as shown there on the left, on the far left. And then when we add a pillar, we actually see these hybridizations. So this was fantastic news when we first did this, because it tells us that in the nanoscale, within the notion of nanoscale thermal conduction, we can actually see phenomena very similar to what we see in acoustic metamaterials. We see these localized modes, and we see the hybridization. Okay, keeping in mind, of course, that we don't want that to be, we don't want these scattering events to be extreme. We would accept just a bit of that on moderation for the very reason I just mentioned, and that is to keep the wave character still intact for all practical purposes. Okay, so that's really the fundamentals of the problem, but there's more to it, because it's at a nanoscale, the physics is very rich. It is inherently size dependent in many ways, in several ways, at least 2 ways. So an important size limitation on the physics of the problem is again the notion of lifetimes. So I'm going to try to demonstrate it here by some images. So we can see in the literature on the left there, this is some analysis obtained by quantum mechanical simulations, so more accurate than the type of simulations we do. We do empirical type interatomic potential MD-based simulations. So these quantum simulations were done for bulk silicon, but they are quite representative to what we're looking at still. They show us that the distribution of phonons that carry heat, which is a population as shown from the Boltzmann transport equation, it's a population that really contributes to the heat transfer. So when we look at that population and we look at the distribution of wavelengths and mean free paths in that distribution, we find that there's a decent spread. So if we specifically look at the mean free path, so for example, this green line here represents 1 micron, and even as big as 1 micron, we can see that a good portion of the mean free path distribution is on the left to it. So that implies that a nanostructure on the order of a few hundred nanometers will indeed allow quite a bit of wave effects to take fold. So we can visualize that. So the mean free path can be related to the lifetime using the Brooke velocity. And if we take that range of mean free path and draw it just to get an idea within a cross section of a pillared membrane, an MPM, if that range is small, as shown there, then effectively all the resonances and all the boundary effects will not take part, and effectively we just have bulk silicon, a huge piece of bulk silicon. On the other hand, if we reduce the size of the configuration such that it within the realm of the mean free path, then we turn our silicon into a totally different material, fundamentally different material, which we can call nanosilicon. So this is one aspect. So what the take-home message here, that in order for an nanophononic metamaterial to work, it cannot be too large in size. For silicon, it can be relatively large in the order of a few hundred nanometers, but certainly not microns and above. Okay, so that's one aspect of size effects. The other aspect is equally as subtle, and that is this notion of resonance hybridizations that we're talking about, which now I can call phonon-vibron coupling. It has to be prevalent in order to get our effect. So that naturally invites us to look at the density of states of each, the membrane portion and the pillar portion, and see how they conform. If they're not conforming, if the distribution is not conforming, that tells us we're not really getting a lot of that effect. And in fact, they're not. So that's not good news to start with. If you look at the vibrons distribution, in blue and the phonons in red, they're not matching very well. So this let us scratch our heads for a bit, my students and I. We spent a couple of years really just examining that subtle aspect of size effect. Obviously, we want to go to large sizes because these MD type sizes are too small for practical purposes. So what we've done here is we enlarge the size proportionally, and we have here a parameter called VR, which is the volumetric ratio, which is the volume of the pillar compared to the base. And so by enlarging proportionally, we're keeping VR constant to 0.11 in this case. And sadly, that problem gets even worse. So we have a metric here, R, that is a measure of how conforming the density of states are. And we see that they actually, the reciprocal of that, we see that that measure increases, which suggests that the conformity actually decreases because that measure is a reciprocal of the conformity. So that was yet another blow to this concept. But then luckily, we actually found a way out. We realized that if we increase the size in a manner such that the pillars grow in size as we increase in size conceptually in our modeling, if the pillars increase at a higher rate, so that's what we call vibrant compensation, we actually get strikingly good results. We see that as we increase, we reach a point where the conformity is almost perfect. So you see that metric gets smaller and smaller, and the red and the blue curves are matching really perfectly. So with that, then we're able to optimize the design. So we're able to optimize the reduction in the groove velocity because the higher the conformity, the more the resonance hybridizations, the more that we get from those two underlying effects, the groove velocity reduction and the mode localization. So explicitly, we can measure this. So this is a measure here. G is a measure of the collective or average groove velocity across the whole spectrum. Blue is a uniform membrane, which is always our reference case that we compare with, and red is an MPM. And we can see as we increase with vibrant compensation, we get more and more groove velocity reduction. That measure there, GR, which goes from 0.5 to 0.11. So that's excellent. The other thing is the second factor, which is the mode localization. So that's yet another factor. In the interest of time, I won't dive into the details there, but it's based on taking the mode shapes and doing dot products. And that factor, again, if you wanted to get less and less because it's a measure of how much the modes are localizing in the pillars. And again, we see that as we increase the MPM at a rate where the pillars are increasing at a larger rate, we get more and more reduction in that factor, which implies more and more localization, which would imply stronger and stronger reduction in the thermal conductivity. So these two elements really allowed us I want to use the word nail it, because we were able then to find a configuration that allows us to have exceptionally strong reduction in the thermal conductivity. So keeping in mind that silicon, bulk silicon in room temperature has a thermal conductivity of roughly 140 watts per meter Kelvin, we were able to show that by adding a pillar with a height to membrane thickness ratio of 60, we can go down by an order of magnitude, as shown there. And this is, as we vary some parameters, the membrane thickness and so on. And in fact, if we add pillars on both sides, we add the effect. So it becomes even more, it's additive. And we were able to show a 2 orders of magnitude reduction in the thermal conductivity by this phenomenon, which is very useful for thermoelectrics, as I'll explain shortly. We started experimental work with my collaborator, Dr. Chris Burtness at NIST, just next door here in Boulder. And we're examining different configurations. This one I'm showing you here is based on growing gallium nitride pillars instead of silicon pillars, which is totally fine. And by molecular beam epitaxy, and we've started examining the thermal conductivity here using Raman thermometry. And we can see that as we increase the height of the nanopillar, the thermal conductivity reduces. We're getting a 25% reduction here, not as strong as what we got with the MD, but this is because in this particular case, we haven't optimized the MPM design, but this was just proof of concept. I want to quickly also contrast with nanophononic crystals, because nanophononic crystals are phononic crystals at the nanoscale, where basically you depend on the notion of Bragg scattering more as the prime mechanism for opening band gaps and flattening curves and so on. So we compared MPMs with nanophononic crystals in this review article. I should make a side note that notice here that I haven't talked a lot about band gaps. In fact, I haven't talked about band gaps at all, and that's because we're not interested in band gaps in this work. We're interested in reduction of the group velocity across the spectrum, and we're interested in the localization and the lifetimes. Of course, the band gaps, if they appear, then that's great. But typically at these extremely small scales, when we have atoms and a band structure that has millions of branches, we rarely see band gaps. Okay, so real quick, because I know that I'm getting close to the end of my time here, comparing with nanophononic crystals. So the red curve here is an MPM as shown on the right with a small pillar. The orange is with a slightly longer pillar, so more atoms, more degrees of freedom, more modes, more resonances, more reduction in thermal conductivity. Indeed, as we increase the nanopillar dimension laterally, we find that so how much of the, if you're looking at the unit cell from the top, how much you're covering it with the pillar, that's the x-axis here. As we increase it, we expect more and more reduction in the thermal conductivity, and as we increase the pillar height, we get more and more reduction downwards. Then we have the phononic crystal in blue, which doesn't have a pillar, it has a hole, and you can see there in the diagram on the right. And because of the hole, you get Bragg scattering, and you get even maybe quite a bit of bandwidth scattering, and it beats the MPM, as you can see. However, when we increase the pillar significantly, and we can do that as I showed in the previous work, in the previous slides, we actually beat the MPC. So we get even stronger reduction, even though we don't have holes. So the main body of the membrane, which transports the heat, is intact, and the agent that is affecting the thermal conductivity is something coming from the ceiling. So it's quite intriguing to see this. And in fact, we see that for 79% coverage of pillar or hole, with an MPM, we're getting 0.9% of the thermal conductivity of a pure membrane, whereas with MPC, we're getting 1.5. So we're almost getting double the reduction for that coverage. And another way to look at it, for the same thermal conductivity reduction, we need much smaller coverage of pillar in the unit cell looking from the top compared to coverage of the whole when looking at it from the top. Okay, implications on thermoelectrics. And this is, I'm going to just show this using some cartoons. You know, as I mentioned earlier, thermoelectrics is about conversion from heat to electricity and vice versa. So electrons are important, not just phonons. And typically with in the field of thermoelectrics, especially in the last 20, 30 years, with the advent of nanotechnology, people have been interested in reducing the thermal conductivity using scatterers, because that's the most direct way to cut the lifetimes and reduce K. So the scientists and researchers experimented and simulated a wide range of possibilities where you include holes, interfaces, inclusions, and so on. The problem, however, is that these same scatterers also scatter the electrons. So it really back to square one. And of course, the mean free paths of electrons are smaller, so you can optimize a bit, but that's still limiting. And for the most part, I would say this is why that approach hasn't succeeded in increasing the performance of thermoelectrics. So now, putting things in the context of MPMs, we actually don't need these scatterers, as I've shown, and instead we reduce the thermal conductivity with these pillars. So that's directly, clearly an advantage, because then essentially we have safe haven for the electrons, whereas we're reducing with this vibrant phonon coupling using the pillars that are introduced on the ceiling. We've done, in order to actually see the impact or directly predict the impact on the ZT figure of merit, you need to do either electrodynamic simulations or do experiments that involves electrical measurements. We're pursuing both, but in the meantime, we've done some careful analysis, and we saw that there's experimental evidence in the literature that the mean free path of electrons for silicon at this temperature is roughly on the order of 20 nanometers. So with some projection calculations, we're predicting that with this reduction in the thermal conductivity, especially that the electronic part of the thermal conductivity for silicon is not that high, we're able to project a ZT of 3.1, which would be really a record not only for silicon but for thermoelectric materials in general. And in fact, that aspect of it, this notion of slowing heat without obstructions, was highlighted in a physics article specifically on that aspect because of its implications on thermoelectrics. Okay, lastly, local resonances are utilized, and so that in many ways, I think in our minds makes it a metamaterial, but we might ask also why specifically we can call it a metamaterial, given that we're not really employing the notion of effective properties and so on. So I have a couple of proposed thoughts on that. One of them is when you look at if we add holes in a material, and by the way, I'm including rough surfaces here just to generalize. When we add holes, we have less material, so we have less atoms, so we have less modes in that formula, so we have less thermal conductivity. So one can easily view a trade-off, a classical trade-off. The higher the number of holes, the more the thermal conductivity reduction, and so on. And we can basically live along that line. Also, in parallel, if we add obstacles, we impede and reduce the lifetime, so we impede the thermal conduction more and more. So again, we can envision a classical trade-off where if we plot the thermal conductivity reduction by the 1 over the number of scattering, so we'll see that as we increase the scattering, the reduction will increase, and as we reduce the scattering, the reduction will decrease. So these are the two classical trade-offs. But now let's see what we're able to achieve with MPMs. We're able to actually increase the reduction in thermal conductivity without adding holes, in fact, by adding material. And we're able to increase the reduction in thermal conductivity without adding scatterers, in fact, by adding no scatterers at all. So in this sense, we are entering into the space of unusual properties, which is, of course, what metamaterials is all about. So in this sense, we can call it a metamaterial as well. Since we've proposed the idea in 2014, a few groups been creative and coming up with other configurations. So, for example, you can consider nanowires with stubs or pillars or discs, and that will give you the same effect. In fact, you can have in bulk, you can have a region that is amorphous, and waves will localize there, and effectively that has been shown that it will also give us these vibrons, and in a way that's also an MPM. Others have looked at graphene, including those buckyballs or even nanotubes, and clearly you can see there on the right these resonance hybridization. So you can realize that not just in silicon, you can realize it in other materials and in different configurations and so on. Okay, so I was a little bit worried about time, but fortunately I reached the end here. So this is just a summary of the key results that I shared with you today. The notion of a nanophononic metamaterial. It's a nanostructured material that exhibits full spectrum, and I emphasize, in silicon, the full spectrum spans up to 17 terahertz, and in principle, we're utilizing the local resonances across this entire spectrum to reduce the thermal transport. It's a fundamentally different set of mechanisms compared to electromagnetic and acoustic elastic metamaterials for the various reasons I explained. And upon projection, and this is of course still to be validated, there is good prospects of getting exceptionally high performance for thermoelectric energy conversion. And for your interest, these are a few references we have over the past few years on this topic, including a book chapter that appeared in the Handbook of Materials Modeling. And specifically, I wanna maybe highlight this last one, which is a review article where we reviewed MPMs, and to put it in context, we compared them to nanophononic crystals, and hence some of these slides that I showed you. And finally, you can find that article in this special issue of Advanced Functional Materials. So that's all I have for today, and I hope we'll have some time for questions.